All right, today is what's the date? 23rd, I think, April today. You got your exam 3 coming up next week. Exam 3 is going to be next Wednesday. And I guess that should be May 2nd. Today's April 23rd. Yeah, that should be May 2nd. It's going to cover the main content, at least, is going to be chapters, well, the end of group theory, for sure chapter 11, the basics of that. We only did the most basic kind of problems in that. Maybe a little bit of chapter 10 on group homomorphisms through chapter 18. I'll say chapters 10 through 18. Okay? So again, last Wednesday and last Friday, and today and this Wednesday, we're sort of doing chapters 14, 15, 16, and 17, again, this holistic approach. I probably will start chapter 18 a little bit on Wednesday. And then Friday for sure is chapter 18. Monday of next week, we will be reviewing everything and getting ready for the exam on Wednesday. Friday of next week, I will not be here, so you will have no class, though I will make a lecture, a video, outside of class, probably Thursday, May 3rd, I'll make an extra lecture. That will mean you will not have to come to class on Friday, May 4th, and there will be no quiz for that one. And then when you come back, that lecture, that extra lecture that I make, will be on chapter 19. And then the last 2 weeks of class will be during chapters 20, 21, and 22 over those 6 class periods, and definitely there's enough content there that it will take 6 class periods for those 3 chapters, including reviewing on the last day of class. Okay? So that's what's to come. All right, what's the plan for today? Ring homomorphisms, long division and synthetic division. Do another example of that. This time we'll do it in mod P arithmetic. Some proofs of facts in polynomial rings. And then in lecture 28b, we'll come back to chapter 17 again, irreducibility and reducibility over, well, we've done fields already, but technically you can talk about that over integral domains. Some theory and some examples. Okay? So let's review ring homomorphisms. So these 3 slides I'm going to show you is what I showed you at the end of class on Friday. You don't have to write this down. Maybe you prefer sitting and thinking. There might be a few extra things I'll write down that might be worth you writing down. But probably it's better for you to just sit and think, okay? You got 2 rings. That means you got 2 operations in each ring, addition and multiplication. You want ring homomorphisms to be the natural generalization of group homomorphisms. You want them to be operation preserving, not just with respect to addition, but also with respect to multiplication. I call that doubly operation preserving. So phi of A plus B should equal phi of A plus phi of B. And phi of A times B should equal phi of A times phi of B. And as I remarked on Friday, the pluses and multiplications are done in each ring respectively appropriate. A ring homomorphism that is both one-to-one and onto is a ring isomorphism. And again, just for reminders, I think there are a couple of you in here who might be interested in graduate school at least. One-to-one is synonymous with injective, onto is synonymous with surjective, and when you're both injective and surjective, it's called bijective. But I'm not going to quiz you or test you on those words. Okay. I showed you a commutative diagram last Friday as a way to visualize this. Again, the book has a couple pictures. Well, has one picture that helps you visualize the operation preserving properties. I'm thinking of the one on page 264. Okay. I drew another kind of picture on the board that, again, if you're thinking about grad school, you're going to see commutative diagrams if you're thinking about grad school in math. Examples, again, a natural ring homomorphism from Z to Zn. By natural, I mean it's sort of like one of those situations where it's kind of like the only thing that you could naturally think of. What's the most natural kind of mapping? It's an appropriate word to use. Take an arbitrary integer k. I want to map it to Zn. What's the most natural thing to do? Well, mod it by n. And again, the properties of modular arithmetic from chapter 0 are what helps you verify this is a ring homomorphism. There are many natural ring homomorphisms from the ring of polynomials with coefficients in the real numbers to the real numbers themselves. This is supposed to be the real numbers here, not just a boldface. For any real number, you can define a ring homomorphism from this ring of polynomials to the reals by this kind of formula. The most common thing to use for a is 0, but theoretically you can use any value of a that you want. What's the verification that this is a ring homomorphism? It's really, again, one of those things that's almost too easy, that you're like unsure that you really proved it. You apply this thing that we're saying is going to be a ring homomorphism to a sum of two functions, that sum of two polynomials. What does that mean? It means by this formula that you've got to take a and you've got to plug it into the sum of those two polynomials. So this is by definition of phi sub a. But also by definition of phi sub a, it's just, again, almost too easy. F of a does equal phi sub a of f of x. And g of a does equal phi sub a of g of x. We've got that. That's the definition of phi sub a as well. Again, these additions are technically done in different rings. This is an addition of polynomials in the polynomial ring. This is an addition of numbers, right? The codomain is the set of real numbers, which is a ring. It's a field, even. Under ordinary addition and multiplication. That's a sum of two numbers. For any fixed a and fixed f of x and fixed g of x. The verification of being operation preserved for multiplication is basically the same thing. Just change the pluses to times. We usually don't even bother putting the dot in there, but I will for emphasis. Okay? It's, again, almost too easy. That's confusing. You're like, am I really done? Is that it? And the answer is yes, that's it. If a does happen to be 0, again, that is the most common case. Then you're evaluating f of 0, which is the same as the constant term of the polynomial. A sub 0. Right? If a sub 0 represents the constant term of the polynomial f of x, then f of 0 is going to be a sub 0. And that's the most common thing to think about with this example, but it's not the only thing you have to think about. This ring homomorphism right here is going to come up in something else we're going to talk about in lecture B today with something called the mod P irreducibility test. Given a ring homomorphism from R to S, there's a natural induced homomorphism, a homomorphism that comes from the original one. It's based on the original one. Call it phi bar. From this polynomial ring to this polynomial ring. Polynomials with coefficients in R, polynomials with coefficients in S. Take an arbitrary polynomial with coefficients in R, those a's are in R, map it to the natural corresponding polynomial with coefficients in S. These phi of a's are elements of S. And yeah, if for example, you've got a polynomial 5x squared plus 3x plus 7 in Zx. Z, of course, is an integral domain, but not a field. That's okay, it is a ring. Again, there's this natural homomorphism from, say, Z to Z2, for example, that maps every integer to what it equals mod 2. It maps all the even integers to 0, and it maps all the odd integers to 1. That induces a phi bar from the ring of polynomials with coefficients in Z to the ring of polynomials with coefficients in Z2. And what would phi bar in particular do to this particular polynomial? You just got to model those coefficients by 2. It's going to map it to x squared plus x plus 1 in Z2x. Okay, so that's a natural thing to do, and it's just something we're going to use with this mod P irreducibility test from chapter 17. Identify the possible ring homomorphisms from Z20 to Z30. We talked about this last time as well. And you thought about it for your homework, actually, although you didn't think about this particular example except with the completion. I think that was on the completion problem, not the graded one. Again, ring homomorphisms are group homomorphisms. So based on what you learned back in chapter 10, and since Z20 and Z30 are both cyclic, it's enough to decide what the homomorphism is based on what it maps 1 to. And if you say it maps 1 to some number A in Z30, what are the possibilities for A? 1 here is in Z20. Well, a property of group homomorphisms from chapter 10 is that the order of A in Z30 has to divide the order of 1 in Z20. The order of 1 in Z20 is 20. So the order of A in Z30 must divide 20. That was a property of group homomorphisms, chapter 10. It's got to be 1, 2, 4, 5, 10, or 20. But A is an element of Z30. As a group element in Z30, it's got to have an order that divides 30. This also divides 30 by Lagrange's theorem. So, combining these two facts, it's got to, the order of A has to divide both 20 and 30. I'm talking about additive order here as a group element under addition. What are the only numbers that divide both 20 and 30? It would be 1, 2, 5, and 10. That doesn't mean those are what A equals. Those are the possible additive orders of A. If the order of A is 1, then A would be 0, right? The identity, the additive identity. If the order of A is 2 in Z30, A would be 15, right? The order of A was 5. There's actually 4 possibilities for A in Z30, or what? 6, 12, 18, 24. Right? Those would be the elements of order 5 in Z30. And if there was order 10, the elements of order 10 in Z30 would be 10 and 20. But you also learned, both from the reading and from your assignment, that because phi is a ring homomorphism, A squared has to equal A. A has to be an idempotent. Remember that in the assignment? Since A equals phi of 1, which is phi of 1 times 1, and since phi is operation preserving with respect to multiplication, this has got to be the same as phi of 1 times phi of 1. In other words, A squared. A has to equal A squared. So to be a ring homomorphism, in addition to a group homomorphism, it reduces the possibilities. You got to look for idempotents among the numbers that I mentioned. What did I mention? 0 has order 1, 15 has order 2, elements of order 5 were 6, 12, 18, 24, and the elements of order 10 were 10 and 20 in Z30 here. The fact that it was a group homomorphism, then it was one of these 1, 2, 3, 4, 5, 6, 7, 8 possibilities, but not all of those are idempotents. 0 is. I'm not going to take the time to find the others because I'm having to multiply and do mod 30. Maybe think about 15. 15 squared is 225. Mod 30 would be 15. 15 is an idempotent. 15 is a possibility. Idempotents. I think there might be one or two others. Actually, 6 is a possibility. 6 squared is 36, mod 30 is 6. 6 is an idempotent. Not all of those are idempotents. 10 is. I was thinking not all of them are idempotents. Let's see. 20 squared is 400, 400 mod 30 is what? 10? Mm-hmm.
Aren't they elements of order 10, not 10 and 20? Aren't they like 3 and 9?
Or I messed it up, didn't I? Sorry about that. Thanks for catching that. Yeah, elements of order 10 would be, yes, 3, 9, etc. Yeah. Sorry about that. Why was I thinking 10 and 20? For some reason, that made me think about elements of order 3. I have no idea why. Maybe my mind got fixed on the 10, even though with these other ones I was not making a mistake. Okay, but again, you're looking for idempotents. Thanks for catching that. Similar kinds of other properties of ring homomorphisms. All the properties of group homomorphisms carry over with respect to addition because, again, ring homomorphisms are group homomorphisms under addition. In addition, I mentioned these quickly last time. I'll mention them quickly again today. Images of subrings are subrings. Images of ideals onto ring homomorphisms. You might want to think about this one. That might make a good test problem, I'm thinking. It's a possible test problem. Images of ideals onto ring homomorphisms are ideals. Why does it have to be onto? I think this is one of the completion problems I made key for as well. Pre-images of ideals are ideals. It doesn't have to be onto there, evidently. Why does it not have to be onto for a pre-image of an ideal to be an ideal? These are things you should look into if you haven't. Think about it. The image of a unity under a non-trivial onto ring homomorphism is a unity. Why does it have to be onto there? Kernels are ideals. You proved that for today on your assignment. And ideals are also kernels. I guess you proved that one too. There is a first isomorphism theorem for rings. The group first isomorphism theorem was on exam 2. Okay, so I guess we did get through chapter 10 in exam 2. I did say it's a possibility for exam 3 here, and I suppose most likely, as far as exam 3 goes, knowing chapter 10 is good for chapter 15. So it's still worth reviewing. And again, a natural homomorphism from Z to any ring with unity. R is an arbitrary ring with unity. You should know what that is. That maps an arbitrary integer n to n times 1, meaning, again, if n is positive, you add 1 to itself n times. If n is 0, you just get 0. If n is negative, say -7 for example, what does -7 times 1 mean? Again, that's not the ring multiplication. It means, well, you can write it this way. It means the additive inverse of 1 added to itself 7 times. That's not necessarily the number -1. This is a ring element, an arbitrary ring with unity 1. For example, there's a natural ring homomorphism from Z onto, or not, I shouldn't say onto, into the ring of polynomials with coefficients in Z. It's going to map your arbitrary integer n to the constant polynomial, really. N times 1 is going to be the constant polynomial n. Here I'm thinking of this n as being a number. Thinking of that n as being a polynomial, a constant polynomial. Number, a constant polynomial. And final fact here, worth remembering, any ring with unity contains a subring, either isomorphic to Zn or to Z. And if the ring has characteristic 0, it's going to be a subring isomorphic to Z. If it's got characteristic n, it's going to be a subring isomorphic to Zn. Long division and synthetic division in polynomial rings over fields. In other words, where the division algorithm applies, we're assuming the ring is a field. Do an example here in a minute, but a few general comments I want to make about this. And a word of encouragement. I hope it's encouraging at least. Don't be afraid to use these tools, even in such an abstract class. Okay? They are very useful. And in fact, these tools saved me. Okay, God saved me, saved my soul, but these tools helped save me, with God's help, in graduate school, along with much prayer, perseverance, my work, waiting on God, and help actually from Eric Gossett. I was in grad school at the U of M, and I was having trouble. In graduate school in math, at least, you have these preliminary written exams on various subjects, and one of them was abstract algebra. And I was having a lot of trouble with that exam. They give you more than one chance to pass it. I was doing very poorly my first 3 times taking it. Okay. What was my problem? My problem was I was too focused on memorization. Okay. Now I do have you memorize in here to a degree because I think there is some value in it. It's not completely worthless. I think it does help bring tools to mind, but it's not enough. It's not sufficient. You might say it's necessary, but not sufficient. To be good at those exams, I needed to solve lots of problems. Now, I did practice some old exam problems for those written exams, but they were really hard, and you know what happened? I just gave up. I'm like, oh, I hope memorization will help me enough. And it never did those first 3 times. But I'm like, okay, I only had 1 more chance to pass it. I had 4 chances total to pass it. And my first 3 scores were really bad, okay? I won't say what they were, but they were bad. I like, okay, I had a summer to study for it. So I did what I knew I should. I tried working on those old exams problems, and I tried persevering. Okay, God, help me through it. Help me solve these problems. And if I can't, I guess I'm not going to be in grad school anymore. And then I wouldn't be here today. I'm not saying this is guaranteed to happen, but I do feel like God helped me be patient, persevering, and I did have success finally by the end of the summer solving those really hard problems. And part of the key was doing long division and synthetic division, and Eric Gossett helping me with that. And I finally solved those problems by the end of the summer, and I got like a super high score the 4th time, like higher than anybody ever really gets. Not that I'm trying to brag or anything, but that's just what happened. It was like the problems matched up with what I had just figured out. It was amazing. So not a guarantee that that will always happen, but it did happen for me, and in many situations, certainly perseverance and hard work does, and waiting on God does help. Especially we're feeling comfortably using these tools over ZP, whereas P is prime. Let's do an example. I'll go ahead and again write it as a division. So we want to take x cubed plus 2x squared plus x plus 2 and divide it by, oh, how about x plus 1 over z3, or in z3x, which is a situation where the division algorithm applies because z3 is a field. Let's do it with long division first. Go ahead and write it with the thing you were dividing into underneath the division symbol kind of thing. And the thing you're dividing by, you never remember what to call those, dividend and divisor, I forget which one goes where. Over there, multiply, ask yourself, what do I need to multiply the highest power there by to get the highest power here? I need to multiply by x squared. Then multiply x squared times x and 1 and put the answer down here. X squared times x is x cubed. X squared times 1 is x squared. Subtract. We are going to do mod 3 arithmetic here. We subtract 2 minus 1 is 1, as usual. So nothing too unusual so far. Maybe the mod 3 arithmetic is kind of trivial here. Can I make this a bit more interesting? Oh well, let's just see what happens. What do I need to multiply the x by to get the x squared? Multiply by x. And go ahead and do that multiplication again. Subtract. Get cancellation. Okay, it wasn't too interesting as far as the mod 3 arithmetic there. That's the danger of doing arbitrarily chosen examples. There's your remainder. It's less than in degree than what we were dividing by. Or it could have been 0. And again, 0 doesn't have a degree. Now what does this mean? It means x cubed plus 2x squared plus x plus 2 in mod 3 arithmetic is equal, as it would be in ordinary arithmetic because we didn't do any modding, to x plus 1 times the quotient x squared plus x plus the remainder 2. Should always be able to check it by multiplying things out. Foil that out, you're going to get x cubed plus x squared plus x squared plus x plus 2. And again, nothing really fancy is happening in mod 3 arithmetic here. This would be true over z as well as z3. That's the danger of doing arbitrary examples. If we were doing mod 3 arithmetic, and in the subtraction we ended up doing a 1 minus 2, for example, that's the same as negative 1, but in mod 3 arithmetic that's the same as 2. The added inverse of 1 is 2. Mod 3, so we would have had to have done something like that. And if we had had x squareds in front of those, these, or next to them, x squareds would be next to that too. What's synthetic division? Synthetic division, first of all, is when you are dividing by a linear polynomial that's monic. The coefficient of the highest power is 1, the leading coefficient is 1, as we are here. Linear and monic, leading coefficient of 1. And it's similar to long division, except you don't bother putting the x's in here. You just put the coefficients. And it's traditional to write this as x minus something. And if I'm going to write it as x minus something, the minus would have to be minus negative 1. which in mod 3 arithmetic is the same as x minus 2, mod 3, and you put a positive 2 over here. Dividing by x plus 1 in mod 3 arithmetic is the same as dividing by x minus 2. Or you put a positive 2 here. 2 is a root of x plus 1, a 0. That's what you put here. You don't go down a real long way with this. You only make it a small amount here. You bring this first coefficient straight down. You do a multiplication just like we did with the long division, but instead of subtracting, you actually add. And it works. Not explaining why it works. Bring the 1 down, multiply. 2 times 1 is 2. Unless I'm making a mistake here. Okay, I think we're okay. Add 2 plus 2 mod 3 is 1. Multiply 2 times 1 is 2. Add 2 plus 1 mod 3 is 0. Multiply 2 times 0 is 0. Add 2. This last thing here, when you divide by a linear polynomial like this, is the remainder, and it will be constant because the degree of the remainder has to be less than the degree of the thing you're dividing by, or it has to be 0. Look at these other numbers. They are the coefficients of the quotient here, x squared plus x. 0 is the constant term. 1 times x, 1 times x squared. Those are the coefficients of the quotient, x squared plus x plus 0. And the thing here is the remainder. Quotient is x squared plus x. Those coefficients. You do need to make sure you put zeros if there's a term that's missing. If we didn't have an x squared up here, if we didn't have that term, we'd have to put a 0 there. So make sure you pay attention to those kinds of things. Let's not have the whispering in back, because it does get on the video. Thanks. Okay, so we didn't really do an ideal example, but it is an example. And again, like I mentioned here, you can do mod 2 or 3 or 5 arithmetic in the way you know you already should. Let's go through a proof of something here, and then we will take the quiz after this proof. I'd like to go over a couple proofs. First proof is the proof of the fact that a polynomial degree n over a field has at most n zeros counting multiplicity. Ignore this thing for the moment. On your assignment for Wednesday, you'll be proving the factor theorem and remainder theorem from chapter 16. They're fairly easy proofs, actually, when you apply the division algorithm. So you should find those to be fairly straightforward, and those would be exam-level proofs of the factor theorem and remainder theorem. This proof's a little harder. It involves induction. You got an arbitrary polynomial degree n over a field. Show it's got at most n zeros counting multiplicity. So it's going to be true, as you already knew before this class, over the reals and over the complex numbers. But it's true over any field, is the point. The proof is that by induction on the degree of the polynomial, stating this clearly true for polynomials of degree 0. They don't have any 0. And we are talking about non-zero polynomials there because, again, the 0 polynomial has undefined degree. We're talking about constant polynomials. They don't have any zeros, and therefore this theorem is true in that case. But n being an arbitrary positive integer, we're going to use the second principle of mathematical induction. We're going to assume inductively that the theorem of the statement of the theorem is true for all non-negative integers less than n. We want to show it's true for a polynomial that has degree n. What do? Well, you use the definition, first of all, what it means to have a 0 of multiplicity k. Suppose f of x has a 0, call it a. That's got multiplicity k. K could be 1, could be 2, could be 3. Most typically it's 1. Then what does that mean? By the definition of a being a 0 multiplicity k, we said this was true. That was the definition of being a 0 multiplicity k. Where, it's important to add this extra thing, where q of a is non-zero. So q of x does not have x minus a as a factor, is the idea there. Computing degrees leads to the conclusion that k is less than or equal to n. What do I mean by computing degrees? Well, when you've got a polynomial over a field written as a product like that, on the screen you can say the degree of f of x equals the degree of x minus a to the k plus the degree of g of x. If you think about examples, this makes perfect sense. Okay, and it is true when we're talking about polynomials over a field in general. The degree of f is n, the degree of x minus a to the k is k. These degrees can't be negative, so this allows us to conclude that k must be less than or equal to n. This degree could be 0. G of x could be a constant polynomial. But it can't be negative in degree, so k has to be less than or equal to n. And k plus some non-negative number equals n. N can't be smaller than k. Oh, I guess it's a q of x, sorry. If a is the only 0 of f of x, we would be done. K is less than or equal to n. That verifies the theorem in that case. Otherwise, you got some different 0. If a is not the only 0, then b, since it's not a 0, it's not equal to a, it's not going to be a 0 of x minus a to the k, it's got to be a 0 of q. And it's going to have the same multiplicity as a 0 of q that it does as a 0 of f. Therefore, we can apply induction. We can apply the inductive hypothesis that we made up here to q of x. To say it's got, at most, degree of q of x zeros. And that would mean that n or k, the sum of those multiplicities would have to be less than or equal to n. Yeah, because we're applying the principle of mathematical induction. Q of x would have at most, whatever its degree is, zeros counting multiplicity. Its degree would be n minus k, whatever that happens to be, by applying our inductive hypothesis to that. And that would mean f has at most n zeros counting multiplicity. Okay, so a little bit tricky. If I were to put this on the exam, probably it would be something where I'd give you some help. All right, let's take a quiz.